400 million years ago, Earth was unrecognizable. There were no birds, no dinosaurs, no mammals of any kind. No grass covered the plains because grass had not yet evolved. No flowers bloomed because flowers did not exist. The continents sat in positions so different from today that no modern map would help you navigate them. The sky was a slightly different color. The air had a different chemical composition. And if you somehow stood on the shore of a Devonian sea and looked inland, you would see something deeply alien. Bare red rock stretching to the horizon, broken only here and there by the first tentative experiments in land vegetation. Strange low plants without leaves, without flowers, without roots as we understand them, clinging to the margins of rivers and coasts like pale green shadows of what forests would one day become. But turn around, look at the ocean, because that is where the real story was happening. Those Devonian seas were extraordinary, warm, shallow, teeming with life in forms that had no equivalent before and have had no equivalent since. Armored fish the size of school buses, reefs larger than anything alive today. Creatures so strange that even professional paleontologists sometimes struggle to explain what they are looking at. And somewhere in those warm, oxygen-poor coastal waters, something was happening that would change the history of life on Earth more profoundly than almost any other event in the past 500 million years. Fish were learning to breathe air. Fish were developing limbs. Fish were, slowly and inadvertently, becoming the ancestors of every land vertebrate that would ever live, including us. This is the Devonian Period, 419 to 359 million years ago. 60 million years of extraordinary biological and geological transformation. Geologists call it the Age of Fishes, which is accurate but undersells it dramatically. It was also the age when land was colonized by complex life for the first time. The age when the first forests appeared and nearly accidentally triggered a global climate catastrophe. The age when the basic body plan that you are using right now to listen to these words was first assembled, fin by fin, bone by bone, in the shallows of ancient seas. Before we go any further, if you find yourself drawn into stories like this, please subscribe to this channel. Your support really helps us to continue this work. Thank you. So let's begin where the Devonian itself begins, with geography. Because the first thing you need to understand about this period is that the world looked nothing like ours, and that difference in geography drove everything that followed. 419 million years ago, the planet's land masses were distributed in a pattern that would have made any modern geographer blink and reach for a strong drink. The great supercontinent of Gondwana dominated the southern hemisphere, a vast landmass incorporating what would eventually become South America, Africa, Antarctica, Australia, and India, all welded together into a single enormous block of continental crust centered roughly over the South Pole. To the north, separated by a broad warm seaway, sat a smaller but still substantial landmass called Laurussia, or sometimes Euramerica, comprising the future North America, Greenland, and most of Europe. And between these two giants, in the tropical and subtropical latitudes, where maximum solar heating occurred year-round, stretched the shallow, warm waters of a proto-Tethys seaway, teeming with the life that would define the entire period. The world was warmer than today, significantly warmer. Global average temperatures in the early Devonian ran perhaps 6 to 8 degrees Celsius above our current baseline, which doesn't sound dramatic until you consider what that means for the poles. There were no polar ice caps. None. The Arctic and Antarctic regions were cool and temperate, not frozen. Sea level was dramatically higher than today as a result, possibly 180 meters above our modern coastlines, which means that vast areas of what are now continental interiors were covered by shallow epicontinental seas. Picture a world where the American Midwest is a warm tropical seaway, where the interior of Europe is underwater, where the edges of continents are defined not by towering cliffs, but by gently sloping carbonate banks disappearing into warm blue water. That was the early Devonian, a world of shallow seas, warm temperatures, high CO2, and no ice anywhere on the planet. The CO2 levels are worth dwelling on for a moment, because they were extraordinary by any modern standard. Early Devonian atmospheric CO2 may have been as high as 4,000 parts per million, roughly 10 times the pre-industrial modern level, and nearly 10 times what we have today, even with all our industrial emissions. This was a true greenhouse world, warm and humid at low latitudes, with active weather systems and enormous rainfall events in the tropical zones. The greenhouse effect was running at full power, driven by volcanic outgassing from the active tectonic systems of the time. And the planet was in a warm, humid, geologically active state that would persist through much of the period before being dramatically disrupted in ways we will get to later. Now, with all that warmth and all that CO2 and shallow seas, you might expect the land to have been lush and green. But here is the first surprise of the Devonian, and it is a significant one. For the first half of the period, the continental interiors were largely barren. Not desert in the modern sense, not the wind-sculpted sand dunes of the Sahara, but something stranger and in some ways more inhospitable. Vast plains of bare red and orange rock, chemically weathered, but not biologically weathered, because there was almost nothing alive on land large enough or numerous enough to have much biological impact on the rock. The red color, which is so characteristic of Devonian continental sediments, that geologists in Britain named the period partly from the distinctive red sandstones of Devon in southwestern England, comes from iron oxides. In the presence of oxygen and without significant organic material to consume that oxygen in decomposition, iron in surface rocks oxidized to hematite, painting the landscape in shades of red and orange that would have looked to modern eyes more like Mars than Earth. The atmosphere above this red landscape was breathable in terms of oxygen content, roughly 15 to 17% compared to our modern 21%, which is enough to support active metabolism in the large animals, but enough lower that a modern human transported to the Devonian would feel slightly breathless and fatigued at any significant exertion, something like being at moderate altitude today. But the atmosphere was also different in ways beyond oxygen content. The UV radiation reaching the surface was higher, as the ozone layer, which is produced by oxygen and shields the surface from solar ultraviolet, was thinner in a world with less atmospheric oxygen. And the air smelled different. No grass, no flowers, no pine resin, no soil bacteria producing the characteristic smell of petrichor. Just rock, water, occasional primitive plant material at the water's edges, and the chemical signatures of a geologically active world. Strange and alien and silent in a way that a modern landscape never is. But even as the continental interiors lay bare, dramatic geological events were reshaping the planet's architecture. The collision between Laurussia and a series of smaller continental fragments was building mountains on a scale that rivaled anything in the modern world. The Caledonian orogeny, which had begun in the Silurian period just before the Devonian, was reaching its climax. The land masses that would become Scotland, Norway, and the northeastern coast of North America were being welded together by collision. The oceanic crust between them subducted, the sediments scraped off and thrust upward into mountain ranges that in the early Devonian were possibly as high as the modern Himalayas. These Caledonian mountains, long since worn to stubs by 400 million years of erosion, their remnants now forming the gentle rounded hills of Scotland, the Scandinavian fjord country, and the Appalachians of eastern North America, were in the early Devonian fresh and dramatic, their peaks dusted with snow despite the overall warmth of the climate at lower elevations, their flanks shedding enormous quantities of sediment into the surrounding seas and continental basins. The rivers draining these mountains deposited the red sandstones that now give the Devonian its characteristic color in the geological record. They were building the geological archive of the period even as the period itself unfolded. And then there is the ocean. Because while all of this geological activity was reshaping the land, the Devonian seas were undergoing their own extraordinary transformation, and this is where the period earns its popular name with complete justification: the Age of Fishes. Because the Devonian oceans were dominated by fish in a way that has no parallel in the history of life, a radiation of vertebrate diversity so rapid and so comprehensive that it reshaped marine ecosystems entirely and set the stage for everything that followed on land. Fish had existed before the Devonian. The Silurian and Ordovician periods had their jawless fish, the agnathons, filter feeders, and small predators that shared the seas with invertebrates. But they were minor players in a world dominated by invertebrates. The Devonian changed all of that. With dramatic speed in geological terms, fish diversified into nearly every available ecological role in the marine environment. They developed jaws, which opened up entirely new feeding strategies. They developed paired fins, which gave them unprecedented maneuverability. They grew large, they grew armored, they grew terrifying. And chief among them were the placoderms. The placoderms. If you are not familiar with this group, prepare yourself, because they are one of the most extraordinary examples of evolutionary invention in the history of vertebrates. Placoderms were armored fish, but armored in a way that no modern fish is. Their heads and the front portion of their bodies were encased in rigid, bony plates, articulated at a joint that allowed the head to tilt upward when the fish opened its mouth, effectively increasing the gape dramatically. This was not a minor anatomical feature. It was a revolutionary feeding mechanism. Instead of simply dropping the lower jaw as all modern jawed vertebrates do, placoderms could simultaneously drop the lower jaw and raise the entire head, producing a bite that was mechanically closer to a bear trap than to anything we see in modern fish. The effect was to dramatically increase the force and speed of the bite, making placoderms extraordinarily effective predators, and also, in some species, extraordinarily effective filter feeders, grazers, and bottom feeders. The basic placoderm body plan was versatile enough to support an enormous range of ecological specializations, and during the Devonian, placoderms exploited virtually all of them. They were the dominant vertebrates in the world's oceans for the entire period, diverse, abundant, and in many cases, very large. And none was larger or more formidable than Dunkleosteus terrelli. This animal deserves to be far more famous than it is, because by any reasonable measure, it was one of the most impressive predators in the history of life on Earth. Dunkleosteus was a placoderm, but a placoderm scaled up to something approaching nightmarish proportions. Estimates of its total length vary because we only have the armored head and front section preserved in most specimens, and the posterior portion of placoderms was unarmored and soft, leaving little fossil record. But based on the scaling relationships that exist in related species, where we do have more complete material, Dunkleosteus is thought to have reached lengths of 6 to 8 meters, roughly the size of a large great white shark. The head alone could be 1.5 meters long, and that head was encased in bone, not scales, with 2 pairs of interlocking bony blades where other fish have teeth. Not teeth, blades. Sharp, self-sharpening bony blades that sheared against each other like scissors, and could, based on biomechanical modeling of the jaw mechanism, generate bite forces of up to 5,500 newtons at the tip of the blades and over 7,000 newtons at the base. To put that in perspective, a modern great white shark generates bite forces estimated at around 18,000 newtons. But the great white is substantially larger. For its size, Dunkleosteus had one of the most powerful bites of any animal that has ever lived. It could bite through virtually anything in its environment. It could bite through the armor of other placoderms, and the evidence suggests that it did, regularly, because Dunkleosteus fossils are frequently found associated with regurgitated, half-digested remains of other armored fish. Dunkleosteus, it seems, would eat anything, swallow the armored portions, and then vomit them back up when its digestive system couldn't process the bone and plate. Charming creature. Absolutely dominant predator of the late Devonian seas. But here is something about Dunkleosteus and the placoderms that was not known to science until 2008, and when the discovery was announced, it genuinely shocked the paleontological community. Because it turned out that placoderms were not just the most fearsome predators of the Devonian seas. They were also, as far as we can tell from the fossil evidence, the inventors of sex. Not reproduction in the general sense. Life had been reproducing sexually for hundreds of millions of years before the Devonian. But internal fertilization, copulation, the physical act of one animal transferring genetic material directly into the body of another. That, the fossil evidence now strongly suggests, was invented by placoderms, and the evidence came from the most unexpected place imaginable. In 2008, paleontologist John Long and his colleagues at Museum Victoria in Melbourne were examining a spectacularly preserved placoderm specimen from the Gogo Formation in Western Australia, a site famous for producing three-dimensionally preserved Devonian fish in remarkable detail. Inside the body cavity of one specimen of a placoderm called Matapicius attenboroughi, named in honor of David Attenborough, they found something extraordinary. A tiny, perfectly preserved embryo connected to the mother by a mineralized umbilical cord. This fish, 380 million years old, had died while pregnant. And the presence of an embryo with an umbilical cord meant something profound. This animal was not laying eggs and fertilizing them externally in the water, as most fish do today. It was carrying its young internally, nourishing them through a placenta-like structure, giving birth to live young. It was viviparous in exactly the way that sharks and some modern fish are viviparous, and in a broader sense, in the way that all mammals, including humans, are viviparous. For internal development to occur, internal fertilization must have occurred first. There must have been copulation. Male placoderms, subsequent research revealed, possessed claspers, intromittent organs used to transfer sperm internally, structures directly analogous to those found in modern sharks and rays. Female placoderms had corresponding anatomical structures for receiving them. The placoderms were not just fish. They were, in a meaningful biological sense, the first animals we know of to have sex in the way that we understand sex. The direct physical transfer of genetic material from one individual to another within the body of the female, followed by internal development of the offspring. Every vertebrate that reproduces by internal fertilization today, every shark, every reptile, every bird, every mammal is using a reproductive strategy whose origins trace back to those armored Devonian fish. Think about what that means. The placoderms are extinct. Every last species gone at the end of the Devonian. They left no direct descendants. And yet the reproductive strategy they pioneered, the fundamental biological innovation of internal fertilization and live birth, survived them, was inherited by or independently evolved in the lineages that followed, and is now the reproductive method of the majority of complex vertebrates on Earth, including every human being alive. The placoderms invented something so successful that even their extinction could not extinguish it. They are gone, but the act they invented is still happening, billions of times every year in every corner of the world. 380 million years of reproductive continuity, traceable in a straight line back to a pregnant armored fish in a warm Devonian sea in what is now the Australian outback. The Devonian did not just give us our limbs and our forests and our coal. It gave us the most fundamental act of vertebrate reproduction. The age of fishes was also, it turns out, the age that invented how vertebrates make more of themselves. And that is not a small thing. But Dunkleosteus was not the only remarkable fish in the Devonian Ocean. Because this period also saw the first appearance and early diversification of sharks, a group that has proven so evolutionarily successful that they persist, largely unchanged in their fundamental design, to the present day. The earliest Devonian sharks were small by modern standards, generally under 2 meters, with skeletons made of cartilage rather than bone, a feature that makes them poor candidates for fossilization, but which occasionally, in exceptional depositional environments, preserves in extraordinary detail. Tiktaalik, one of the best-known early sharks from the late Devonian of Ohio, was a streamlined, apparently fast-swimming predator with a deeply forked tail suggesting high-speed pursuit hunting, large eyes suggesting a visual predator, and teeth that, while simple compared to modern shark teeth, were already distinctly shark-like in their basic architecture. The sharks were not yet dominant in the Devonian, living in the shadow of the far more diverse and often much larger placoderms. But they were present, they were diversifying, and they were establishing the fundamental design that would eventually, after the placoderms were gone, allow them to become the apex predators of the world's oceans for the next 350 million years and counting. The invertebrate life of the Devonian seas was equally extraordinary, though it tends to be overshadowed by the more dramatic vertebrate story. The reefs of the Devonian were dominated not by corals in the modern sense, but by organisms called stromatoporoids, sponge-like colonial animals that built massive carbonate structures in the warm, shallow, clear Devonian seas. These stromatoporoid reefs were enormous. At their greatest extent in the Middle Devonian, they formed reef systems that stretched for thousands of kilometers along the margins of Laurussia and Gondwana. Reef complexes larger in total extent than the modern Great Barrier Reef of Australia, the largest reef system alive today. These ancient reefs were biological construction projects of staggering scale, built over millions of years by organisms that were individually simple but collectively capable of producing structures of continental proportions. They harbored extraordinary biodiversity, crinoids with their feathery arms filtering nutrients from the water, brachiopods with their distinctive two-valved shells covering the sea floor in such density that in some locations they literally pavement the bottom, ammonites, those elegant coiled cephalopods that were just beginning their long evolutionary journey in the Devonian, nautiloids of various forms, trilobites still present though declining from their earlier Paleozoic dominance, sea scorpions called eurypterids, reaching lengths of 2 meters and representing some of the largest arthropods that ever lived. The Devonian Ocean was a complex, layered, diverse ecosystem with multiple trophic levels, complex predator-prey relationships, and a biological productivity that would have been, if you could have looked down from above, visually stunning, the shallow reef zones glowing with color and life in the clear tropical water. And here, at roughly the 8-minute mark of our story, is the first major twist. Because all of that reef abundance, all of that stromatoporoid construction, all of that extraordinary carbonate-producing biological machinery was operating on borrowed time. Not because of anything happening in the ocean itself, but because of something beginning to happen on land. Something quiet, something gradual, something that would not fully manifest its consequences until the end of the period, but something that was already, in the Middle Devonian, beginning to fundamentally alter the chemistry of the atmosphere and the oceans in ways that the reef organisms could not adapt to quickly enough. The forests were coming, and the forests, beautiful and world-changing as they were going to be, in a very real geological sense, catastrophically destructive. But before we get to the forests and their consequences, we need to spend some time on the land itself in the early and middle Devonian, because the story of what was happening on the continents during this period is one of the most remarkable tales of biological colonization in the history of life. When the Devonian opened, the land was not entirely lifeless. Primitive plants had been present since at least the Ordovician, tiny, simple organisms without true leaves or roots, clinging to the margins of water bodies and surviving in a thin zone where moisture was available. By the Silurian period immediately preceding the Devonian, these plants had developed simple vascular tissue, the internal plumbing system that allows water and nutrients to be transported through the plant body, and had reached heights of perhaps a few tens of centimeters. Progress, certainly, but not yet the kind of biological presence that could significantly alter the character of a continent. The early Devonian saw an acceleration of plant evolution that was, in geological terms, explosive. Within the first 20 million years of the period, plants developed true roots, true leaves, true vascular systems capable of supporting significantly larger body sizes, and began experimenting with the structural innovations that would eventually lead to trees. The early Devonian landscape near water bodies went from essentially bare to occupied by plant communities, reaching a meter or more in height, communities that were ecologically simple by modern standards, but represented an entirely new kind of terrestrial ecosystem. These early plant communities were dominated by organisms like Cooksonia, a plant so simple that it barely qualifies as a plant by modern intuitions, a Y-branching stem with spore-bearing capsules at the tips and no leaves whatsoever, and Rhynia, slightly more complex, but still recognizably primitive. They grew in dense mats near water, their root systems shallow and limited, their ability to colonize dry ground minimal. The air around these early plant communities would have been different from the open rock of the continental interior. More humid because the plants were transpiring water. Richer in oxygen very locally because photosynthesis was occurring. And beginning, for the first time in the history of the planet, to develop something recognizable as soil. Real soil, with organic matter from decaying plant material, with mineral particles broken down by root acids, with the beginnings of the nutrient cycling that makes soil a biological system rather than merely a physical substrate. This was new. Before plants, the continents had regolith, chemically weathered rock material, but not soil in the biological sense. The Devonian was when soil was invented, and the invention of soil changed everything about how continental surfaces interacted with the atmosphere and the ocean. By the Middle Devonian, roughly 390 million years ago, plants had made another quantum leap. The first genuinely tall plants appeared, organisms that could be reasonably described as trees, with proper woody stems capable of supporting their own weight to heights of several meters. And then, in the late Devonian, around 380 million years ago, came Archaeopteryx. This is one of the most important organisms in the history of life, and it deserves a moment of proper appreciation. Archaeopteryx was the world's first true forest tree. It had a genuine woody trunk, producing the secondary xylem that we recognize as wood. It reached heights of 30 meters, tall enough to create genuine forest canopy. It had broad, fern-like leaves that created shade beneath the canopy, altering the microenvironment at ground level. And it reproduced by spores, not seeds, which is botanically interesting because Archaeopteryx looks from a distance like a modern tree, but is reproductively still primitive. It spread rapidly across the late Devonian landscape wherever moisture was available, creating the first forests, the first genuinely forest ecosystems, with canopy and understory and forest floor and all the ecological complexity that implies. Standing in an Archaeopteryx forest 400 million years ago would have been a strange experience. The trees themselves would have looked almost familiar, large, with spreading canopy, dappled light reaching the ground through gaps in the foliage. But the ground beneath would have been wrong. No grass, obviously, no flowering plants, no mammals rustling in the undergrowth, no birds calling from the branches. The understory plants would have been primitive ferns and early lycopsids, plants with a distinctly alien architecture. The animals visible would have been small arthropods, early insects, millipedes, and perhaps near streams, the first amphibious vertebrates making tentative excursions onto land. And the smell would have been unlike any modern forest. No pine resin, no flower nectar, no decomposing autumn leaves in the familiar sense. Just green plant material and the chemical signatures of early soil formation. Alien enough to be disorienting, familiar enough to recognize as a forest. And those forests were doing something to the planet that nothing had ever done before on this scale. They were pulling carbon dioxide out of the atmosphere and locking it in the wood. Every tree trunk, every fallen log, every accumulation of leaf litter represented carbon that had been in the atmosphere as CO2 and was now sequestered in organic matter. And the roots of these trees were reaching down into rock and doing something equally consequential. Root acids accelerate the chemical weathering of silicate minerals in rock, and weathering of silicate rocks also consumes CO2, pulling it from the atmosphere and incorporating it into carbonate minerals that wash into the ocean and are eventually sequestered on the seafloor. The Devonian forests were running both of these carbon removal processes simultaneously: direct biological sequestration in wood and accelerated chemical weathering through root activity. And the effect on atmospheric CO2 was dramatic. From the roughly 4,000 parts per million of the early Devonian, atmospheric CO2 dropped steeply through the middle and late Devonian as forests expanded. By the end of the Devonian and into the early Carboniferous period that followed, CO2 may have fallen to as low as 300 parts per million, close to pre-industrial modern levels. This was a fall of more than 90% in carbon dioxide concentration over roughly 30 to 40 million years. And it had predictable consequences for global temperature. The planet cooled significantly. The warm, ice-free Devonian world gave way by the early Carboniferous to a world with polar ice caps, declining sea level, and the beginning of the icehouse conditions that would persist for much of the next 100 million years. The forests didn't just change the land. They changed the planet's entire climate system, inadvertently, as a side effect of their own biological success. But before that cooling became the dominant story, the late Devonians still had remarkable biological events to unfold. And the most remarkable of all was happening in an unlikely setting. Not on the great reefs, not in the open ocean, not in the spectacular placoderm-dominated seas, but in shallow, warm, often stagnant, often oxygen-poor freshwater environments on the continental margins. In rivers, in floodplains, in coastal swamps and deltaic systems where rivers met the sea and created the complex, fluctuating, ecologically demanding environments that would turn out to be the crucible of one of the most important evolutionary transitions in the history of complex life. This was where the lobe-finned fish lived. And the lobe-finned fish were not like other fish. In most fish, the fins are supported by simple rays of bone or cartilage, thin and flexible, attached directly to the body wall, useful for stability and steering, but structurally simple. In lobe-finned fish, the pectoral and pelvic fins, the fins that correspond to our arms and legs, were supported by a completely different arrangement. A single proximal bone connected to the body, corresponding to our humerus in the arm or femur in the leg. Then 2 bones in parallel. Then a series of smaller bones at the end. If that architecture sounds familiar, It should, because it is, in a simplified form, the basic structure of every tetrapod limb that has ever existed. The arm of a human, the wing of a bird, the flipper of a whale, the foreleg of a horse, all of these are variations on the same fundamental design that was already present in rudimentary form in the lobe fins of Devonian fish. We were there, in those fins. We just hadn't been assembled yet. The lobe-finned fish of the Devonian included several major groups, but the ones most relevant to our story are the Ripidistions, a group of predatory lobe-finned fish that occupied the freshwater environments of the Devonian continents. These fish were formidable predators in their own right, large, with powerful jaws and sharp teeth, capable of pursuing and capturing substantial prey. But they were also, in retrospect, caught in an evolutionary situation that would drive them toward one of the most momentous transformations in the history of life. The problem was oxygen. Those warm, shallow, sometimes stagnant freshwater environments where Ripidistions lived were often oxygen poor. The water was warm, which reduces oxygen solubility. It was often rich in decaying organic matter, which consumes dissolved oxygen. And during dry seasons, water levels dropped and ponds became isolated, concentrating whatever life remained in shrinking, increasingly oxygen-depleted pools. For a fish dependent entirely on gills for gas exchange, this was a serious problem. Gills work by extracting dissolved oxygen from water, and when dissolved oxygen levels fall below a critical threshold, gill breathing is simply insufficient to maintain an active metabolism. Many fish species solve this problem by gulping air at the surface, using their swim bladder as a simple lung to supplement gill breathing. Some Devonian lobe-finned fish had developed exactly this capability, a swim bladder modified into a lung-like structure capable of extracting oxygen from air. Combined with their lobe fins, which could prop the front of the body up and allow the fish to press its head against the surface to gulp air. This gave some lobe-finned fish a remarkable degree of tolerance for low oxygen conditions. They could survive in environments that would have killed a typical gill-breathing fish. And then comes Tiktaalik. In 2004, a team of paleontologists led by Neil Shubin of the University of Chicago discovered fossils on Ellesmere Island in the Canadian Arctic that would fundamentally change our understanding of the fish-to-land transition. Tiktaalik roseae, as the new species was named, was a large, lobe-finned fish, probably up to 2.7 meters long, that lived approximately 375 million years ago in what was then a warm tropical river delta system near the equator, now preserved in rocks in the high Canadian Arctic, as a testament to how dramatically plate tectonics has rearranged the world. Tiktaalik was a fish. It had scales, it had fins, it breathed water through gills. But it had features that no fish before it had possessed in such clear form. It had a neck, a genuine neck, with a joint between head and body that allowed the head to move independently, something no ordinary fish can do. Its pectoral fins, the fins corresponding to our arms, had internal bones arranged in exactly the pattern of a tetrapod forelimb, complete with a structure equivalent to a wrist, allowing the fins to be used for support in a push-up position. Its ribs were robust enough to support the weight of the body without the buoyancy of water. Tiktaalik could prop itself up on its forefins and raise its head to look around in a way that was completely impossible for any ordinary fish. Was Tiktaalik walking on land? Probably not in any sustained sense. it was almost certainly primarily aquatic, spending most of its time in the water and using its remarkable forefin anatomy to navigate shallow, vegetated aquatic environments where conventional swimming was difficult, and crawling along the bottom on sturdy fins was more practical. But Tiktaalik represented the evolutionary stage immediately before true land locomotion, the moment when the basic anatomical toolkit for terrestrial movement was assembled but not yet being used for its ultimate purpose. It was, as Neil Shubin described it in his excellent book on the subject, a fish with the beginnings of a neck, a fish with something like a wrist, a fish that could do a push-up. The missing link between fish and tetrapod, found almost exactly where evolutionary predictions said it should be found, in rock of the right age, in the right kind of ancient environment. And close behind Tiktaalik in geological time came the actual tetrapods, Acanthostega and Ichthyostega, both from late Devonian rocks of Greenland, dated to approximately 365 to 360 million years ago, were genuinely four-limbed animals. Not fish with fin-like structures, but animals with recognizable limbs bearing recognizable digits. Acanthostega had 8 fingers on each forelimb. Ichthyostega had 7 toes on its hind limb. The number of digits was not yet standardized at 5, which is the number that most tetrapod lineages eventually settled on. But digits they were, genuine fingers and toes, protruding from limbs with all the basic bones of a tetrapod limb: humerus, radius, and ulna in the forearm, femur, tibia, and fibula in the hind limb. Here comes the twist that genuinely surprises most people when they encounter it for the first time. Acanthostega, despite having 4 fully formed limbs with digits, was not a land animal. It was aquatic, profoundly aquatic. Its limbs, careful anatomical analysis shows, were not capable of supporting its body weight on land for any extended period. Its shoulder girdle was not attached to its spine in the way necessary for true terrestrial locomotion. Its gills were well developed and clearly functional. Acanthostega lived in the water. It probably used its limbs primarily for pushing through dense aquatic vegetation in shallow water environments, or for anchoring itself against currents, rather than for walking on land. The limbs evolved in the water for aquatic purposes before they were co-opted for terrestrial locomotion. The first tetrapods were not land animals that evolved from fish. They were aquatic animals that evolved limbs for aquatic reasons, and only later, gradually, tentatively, and probably in response to specific ecological pressures, began to use those limbs for excursions onto land. This is a profound conceptual shift. Evolution does not plan ahead. It does not build structures for future use. Acanthostega did not evolve legs, because legs would someday be useful for walking on land. It evolved legs because legs were useful in its immediate aquatic environment, for reasons we are still working out in detail. The fact that those legs turned out, millions of years later, to be adaptable for terrestrial locomotion was not a product of foresight. It was an accident of structural opportunity, one of the most consequential accidents in the history of life. Ichthyostega was somewhat more capable of land excursions than Acanthostega, with a more robust skeleton and limb structure, and may have been able to haul itself out of water for short periods in a manner somewhat analogous to a modern seal or mudskipper. But it too was primarily aquatic. The genuine conquest of land, the development of animals capable of sustained terrestrial existence, of reproduction on land, of complete independence from the aquatic environment, would take another 20 to 30 million years beyond the Devonian and would not be accomplished until the early Carboniferous period. The Devonian gave us the limbs. It gave us the basic tetrapod body plan. It gave us the first tentative excursions onto a surface that no backboned animal had ever walked before. But it did not quite give us land animals in the full sense. That was the next chapter, built on the foundation the Devonian had laid. Meanwhile, back on land, the forests were growing, and something was happening in those forests that added yet another dimension to the Devonian's legacy. The forests of Archaeopteryx and related plants were not silent, empty spaces. Life was following the plants onto land, colonizing the new terrestrial environments that plants were creating, and doing so with extraordinary evolutionary creativity. The first terrestrial arthropods, the ancestors of modern insects, spiders, centipedes and millipedes, had colonized land before the Devonian forests arrived, following the early plants into the marginal damp environments near water. But the forests created entirely new opportunities. Forest floors rich in decaying plant material, canopies offering new microenvironments. The complexity of three-dimensional vegetation structure providing ecological niches for animals that could exploit vertical space. The Devonian forests were inhabited by creatures that would look deeply alien to modern eyes. Giant millipede-like arthropods called arthropleurids, which would eventually, in the Carboniferous, reach lengths of 2 meters, were already present in their Devonian precursors. Early mites and collembolans, microarthropods that fed on fungal material and decaying plant tissue, were present in remarkable diversity, as evidenced by their preservation in Devonian amber from sites in New York State. And the fungi. The fungi were perhaps the most important and most overlooked residents of the Devonian terrestrial ecosystem, because fungi were doing something that nothing else could do effectively. They were decomposing dead plant material. This brings us to one of the most startling facts about the Devonian and Carboniferous worlds, one that connects directly to the modern economy in ways most people never think about. The woody tissue of plants, the lignin and cellulose that give wood its structural strength, is extraordinarily resistant to biological decomposition. In the modern world, it is broken down primarily by a specific group of fungi called white rot fungi, which have evolved the enzymatic machinery to digest lignin. But those fungi, or at least their most effective lignin digesting capabilities, had not fully evolved by the Devonian. The biochemical toolkit for efficient wood decomposition was either absent or very limited in the Devonian world. And the consequence of this seemingly minor fungal deficiency was extraordinary. When trees died in the Devonian and early Carboniferous, they did not rot. They fell, they piled up, they were buried by sediment, and they were preserved as organic material in the geological record. Layer upon layer of undecomposed wood, buried and compressed and heated over millions of years, became coal. The coal deposits that powered the Industrial Revolution, that drove the economic transformation of the 18th and 19th centuries, that are still being burned in power plants around the world today. Those deposits are largely the product of Devonian and Carboniferous forests, whose timber could not be efficiently decomposed by the organisms of the time. The Devonian's fungal limitation created the fossil fuel economy of the modern world. It is not a small thing. And now we need to talk about the end of the Devonian. Because the period did not conclude gracefully. It ended in catastrophe, one of the 5 great mass extinctions in the history of complex life, an event so severe that it reshaped the entire trajectory of vertebrate and marine evolution and left a mark in the geological record as clear and dramatic as the asteroid impact that killed the non-avian dinosaurs. The late Devonian extinction, also called the Kellwasser event from the name of the German rock sequence, where it was first clearly documented, unfolded between approximately 372 and 359 million years ago in the final stages of the period. It was not instantaneous. It was a protracted crisis with multiple pulses of extinction separated by intervals of partial recovery, playing out over perhaps 20 million years. But its cumulative effect was devastating. Roughly 70 to 80% of all marine species were lost. The great stromatoporoid reefs, those vast carbonate structures that had dominated Devonian seas for 50 million years, collapsed and did not recover for millions of years. The placoderms, the armored fish that had been the most successful and diverse vertebrates of the Devonian Ocean, went extinct completely and entirely. Not a single placoderm lineage survived the end of the Devonian. The most successful vertebrate group of the period, the dominant predators of the world's seas for 60 million years, vanished without descendant. Gone. What caused it? This is a question that paleontologists and geologists have been debating for decades, and the honest answer is that we probably do not have a single cause. The late Devonian extinction was almost certainly multi-causal, driven by a combination of factors operating simultaneously and interacting with each other in ways that amplified the severity of the crisis. But one of the leading suspects is also one of the most ironic in the history of life: the forests. Those Devonian forests that we have been celebrating as one of the period's great biological innovations, those world-changing ecosystems that invented soil and drove the conquest of land, were also, according to a significant body of evidence, major contributors to the mass extinction that ended the period. The mechanism runs like this. As forests expanded through the Middle and Late Devonian, they did 2 things simultaneously. They pulled enormous quantities of CO2 out of the atmosphere, cooling the planet and reducing the greenhouse effect, as we have already discussed. And they accelerated the chemical weathering of rocks through root activity, which also consumed CO2 and, crucially, released large quantities of dissolved nutrients, particularly phosphorus and nitrogen, into river systems that carried them to the ocean. In the modern world, coastal marine environments that receive large nutrient inputs from rivers develop algal blooms, dense proliferations of algae that consume oxygen as they decompose and create hypoxic, oxygen-depleted dead zones. This process is called eutrophication, and it is a significant environmental problem today in coastal zones affected by agricultural runoff. In the late Devonian, the rapidly expanding forests were, in essence, running a global-scale eutrophication experiment on the world's shallow seas. The nutrient pulse from forest weathering fed algal blooms. The algal blooms, as they died and sank and decomposed, consumed dissolved oxygen in bottom waters. The shallow seas, already warm, and therefore naturally low in dissolved oxygen, became anoxic, oxygen-free, in their deeper portions. And the organisms that lived in those deeper waters, the benthic invertebrates, the bottom-dwelling fish, the reef organisms that depended on well-oxygenated clear water, died at a global scale over millions of years, killing the reefs, killing the placoderms, killing 3/4 of marine species. The cooling from forest CO2 drawdown may have compounded the crisis. Cooling reduces the solubility of CO2 in seawater, which affects ocean chemistry. It affects the distribution and circulation of ocean water masses. It may have triggered the first Gondwanan glaciations, producing sea level drops that exposed and killed shallow reef environments. And there may have been additional factors. Some researchers have pointed to evidence of increased cosmic radiation reaching Earth's surface during the late Devonian, possibly related to a nearby supernova or changes in Earth's magnetic field, which could have increased mutation rates and stressed ecosystems already under pressure from multiple directions. Others have pointed to large igneous province volcanism, the eruption of enormous quantities of lava and volcanic gases from hotspot systems, as an additional climate stressor. The truth is almost certainly that the late Devonian extinction was a perfect storm of environmental stresses, with the forests as one of the most important and most ironic contributors. Ironic because those same forests, by driving the extinction of the placoderms and the collapse of the Devonian reef systems, cleared the ecological stage for the survivors. And who survived the late Devonian extinction? The tetrapods survived. The lobe-finned fish lineages that were ancestral to land vertebrates, already adapted to the oxygen-poor, ecologically challenging freshwater environments that the extinction was partly generated from, pulled through. The sharks survived, their cartilaginous skeletons and ecological flexibility giving them resilience. The ray-finned fish, the actinopterygians, ancestral to the vast majority of modern fish species, survived and would go on to dominate the world's aquatic environments to the present day. The early land plants survived, damaged but present, ready to continue their colonization of the continents in the Carboniferous that followed. The extinction did not end the story. It redirected it. And the direction it redirected toward was, eventually, us. Every land vertebrate alive today, every amphibian, every reptile, every bird, every mammal, including every human being, is a descendant of the lobe-finned fish that survived the late Devonian extinction. More specifically, we are all descendants of the tetrapod lineage that emerged from those Devonian freshwater environments with their proto-limbs and their air-breathing capabilities and their ability to tolerate the kind of environmental stress that the extinction event represented. We are, in the most literal biological sense, children of the Devonian. The period shaped us before our lineage existed, before the first amphibian walked on land, before the first reptile evolved, before the first mammal nursed its young, before the first primate climbed a tree, before the first hominin stood upright on an African plain. All of those events were downstream of what happened in Devonian river systems and coastal swamps 400 to 360 million years ago. Consider what this means at a practical, embodied level. Move your fingers right now. Flex them. Extend them. Feel the tendons pulling, the joints bending. The basic structure of those fingers, the arrangement of bones in your hand, the carpal bones, the metacarpals, the phalanges, is directly homologous to the bone arrangement in the lobe fin of a Devonian fish. Your humerus, radius, and ulna, the bones of your upper arm and forearm, are the humerus, radius, and ulna of Tiktaalik, modified and refined over 375 million years of evolution, but recognizably derived from the same ancestral structure. Your shoulder, the remarkable ball and socket joint that gives your arm its extraordinary range of motion, is a modified version of the articulation between the lobe fin and the body in a Devonian lobe-finned fish. You are, in your skeleton, a Devonian fish that learned to walk, breathe air, grow warm-blooded, develop a large brain, and develop language sufficient to discuss its own evolutionary origins. The Devonian is not ancient history. It is structural biology. It is in your body right now. The rocks of the Devonian are also present in the modern economy in ways that go beyond coal. The Devonian period produced significant petroleum source rocks in many parts of the world. The organic rich shales deposited in anoxic Devonian basins, both marine and freshwater, have in many regions been the source of economically significant oil and gas accumulations. The Antrim Shale of the Michigan Basin, the Marcellus Shale of the Appalachian Basin, both Devonian in age, have been major targets of natural gas development in the United States. The world's oldest oil wells, drilled in Pennsylvania in the 19th century, tapped Devonian reservoirs. The Devonian is literally fueling the modern world, in addition to giving us the body plan to drive the cars that run on that fuel. The period's economic legacy is as tangible as its biological one. The mountains that the Devonian built are still with us too, worn down but present. The Caledonian Mountains, formed by the collision that was happening as the Devonian opened, are today represented by the Scottish Highlands, some of the oldest and most heavily eroded mountain landscapes in the world. The rounded, gentle hills of the Cairngorms and the Northwest Highlands, beloved by hikers and ecologically precious as some of Britain's last near-wilderness areas, are the deeply eroded roots of mountains that 400 million years ago may have been as dramatic as the modern Alps. The Appalachians of eastern North America, their rounded ridges and forested valleys, so familiar to anyone who has driven Interstate 81 or hiked the Appalachian Trail, are the equivalent remnants of the same Caledonian-Acadian mountain-building event on the other side of the Proto-Atlantic. What are now gentle, ancient mountains, worn to a fraction of their original height, were, in the Devonian, fresh and dramatic, shedding the red sediments that filled the continental basins to either side. And the Devonian's legacy in terms of Earth's carbon cycle and climate extends all the way to the present day. The CO2 drawdown driven by Devonian forests was one of the defining climate events of the Paleozoic era, dropping global temperatures from the warm early Devonian baseline into the glacial conditions of the Carboniferous. The coal that formed from those same forests was eventually burned in industrial quantities beginning in the 18th century, returning the sequestered carbon to the atmosphere and driving the anthropogenic climate change we are experiencing now. There is a certain geological irony in the fact that the Devonian forests solved an atmospheric CO2 problem by burying carbon, and that we are now solving an energy problem by digging that same carbon up and burning it, recreating the high CO2 atmosphere that the forests worked for millions of years to eliminate. We are, in a sense, running the Devonian carbon cycle in reverse, and at a pace roughly 100 times faster than the original sequestration occurred. What does all of this add up to? The Devonian Period, 60 million years of Earth history beginning 419 million years ago, was one of the most consequential intervals in the history of life. It was the age when fish became the dominant vertebrates in the world's oceans, and when the most spectacular of them, the placoderms, achieved a level of armored, powerful, biologically innovative diversity that has never been equaled by any other vertebrate group in a comparable time frame. It was the age when the first forests appeared and fundamentally altered the chemistry of the atmosphere, the character of the land surface, the nature of terrestrial ecosystems, and ultimately the trajectory of global climate. It was the age when the first tetrapods, the ancestors of every land vertebrate that has ever lived, assembled their remarkable limbed body plans in freshwater environments and began the tentative, accidental, profoundly consequential process of exploring land. And it was the age that ended in catastrophic mass extinction, wiping out the dominant marine life forms and clearing the stage for the survivors to diversify into the empty ecological space. A diversification that would eventually, over hundreds of millions of years and through dozens of subsequent evolutionary innovations, produce the world we inhabit. The Devonian looks alien. Its geography is unrecognizable. Its biology is unfamiliar in detail, dominated by organisms that no longer exist. Its climate was different from anything in recorded human experience. And yet, it is the period in which the essential foundations of our own existence were laid. Our limbs are Devonian. Our forests are Devonian in origin. The fuel in our power plants is Devonian. The mountains we hike are Devonian remnants. We are, more than we usually realize, a Devonian civilization built on the biological and geological legacy of a world that ended 360 million years ago. Those strange, shallow, warm seas with their armored fish and their enormous reefs and their oxygen-poor coastal swamps. That bare red continent with its first tentative forests and its crawling, air-gulping proto-tetrapods, that geologically active world of colliding continents and building mountains, it was alien. It was strange. It was violent with extinction and brilliant with innovation. And it was, in every meaningful biological sense, the world that made us. The next time you move your hand, remember Tiktaalik. The next time you walk through a forest, remember Archaeopteryx. The next time you fill a gas tank or turn on a light powered by a coal plant, remember that you are burning the wood of trees that fell in a world where nothing had yet learned to rot them. The Devonian is not gone. It is everywhere around you and inside you and under your feet. The age of fishes was also the age that invented us.